And we're up. Okay, so last time I played Turing Complete. Yeah. Last time I played Turing Complete, the game crashed and I was unable to reload the save game. I reported the error after streaming, and about a day later, the game had a patch and my game can load again. So this, I've gone through and looked at some of the things, but this is how we left it last time we were playing. Well, last time I was playing. So if we progress, I haven't made any progress yet, but if we progress, the next level would be this one. Add 5. And we can actually see it, which is good. You have built your computer, but to win the competition you still have to finish the maze. But since you don't know how to program it yet, you are not quite ready for that. So in the meantime, we will have you help out on the ship a little. Using the edit icon program on the program component, edit memory. It could be worded a bit better. Using the edit memory button on the program component, program your computer to read an input, add 5 and output it again. I'm guessing this is your input, that's your output. So we want to read an input, add 5 and then output it. So let's open okay. View instruction definitions. Okay, now I need to remember how our computer works, because obviously the game crashed since the last time. Well, it's been a few since the game crashed. It's been a few days. So if I remember correctly, looking at this, 1 plus 2, well, 1 and 2, whatever math. So we are adding, so it is memory location 1 plus memory location 2 is then placed in memory location 3, and then we can run a decision on it. We don't need to. What we need to do, let's, immediate. Where does immediate go? Was that immediate puts it in 0? So immediate, we want to put 5 in there. So put 5 in immediate. Then copy, that goes in 0. Copy 0 to 1. I am guessing a bit here, but I'm say that instruction runs first, that instruction runs next, and so on. So copy 0 to 1, then copy input to 2. That one. Copy input to 2. So I have 5 in 1, input in 2, that puts it in 3. So then we want to copy 3 to output. No. We do want to copy 3 to output. But first, we need to... Oh, what was that? Add. There you go. We need to add. So move 5 into 1. Move input into 2. Add, which puts the result in 3. And move 3 to output. So... yeah, put 5, I don't know if you can see this. Put 5 in 0, copy 5 to 1, read input, so that wants to go into here, becomes a 3, so put 5 into there, put 3 into slot 2, then add. So we should probably see 8 in 3, that's right. And then it just completed, so it resets everything. So test 1 of 8 completed. Everything passed. So we finished that level. Calibrating laser cannons. On our ship we naturally shoot incoming asteroids with lasers. In order to calibrate said laser, we want you to calculate the circumference of the asteroid using an advanced equation. The circumference. That's just the outer circle. R is the input, and you can approximate pi is 3.14, whatever, so well, we don't have decimal places, floating point numbers in this thing, so send the answer to output when it has been calculated. So 2 pi r we want to multiply r by 6. Also, you now have access to assembly programming. It allows you to add names for instructions, so you can, for example, type add instead of inputting the number 68. Right. Edit watched state, it didn't tell us about that. It seems to be linked to the memories. Edit memory. He's given us some handy instructions, look. So we want to take the input, multiply it by 6, and then put it in the output. So how do we multiply by 6? So first things first, move from input to, let's say, 1. Where's our... okay. Copy input to 1. I'm going to stick with lowercase because the other ones they already exist are lowercase, and I'll follow the pattern into reg 1. Reg 0 to reg 1 and 2. Let's go copy 1 to 2, reg 1 to reg 2, so now if we do add, 3 has double because we've put the same number in 1 and 2 and added them together. So let's move reg 3 to got reg 3 to out. Reg 3 to reg 1, which I'll have to program in the list. Reg 3 to reg 1, add again. Reg 3 now contains triple because we've taken, put it in 1, put it in 2, added them together, then put it back in 1, so 1 contains double of what it started with, then added them together, so 1, which was double, plus 2 is now triple, so that's times 3. So if we again do reg 3 to reg 1, but we also do reg 3 to reg 2, which I'll have to program, then add reg 3 to out should now contain 6 times the original number. Of course, there are other ways of doing this. You could just keep moving 3 to 2 and adding 1 each time, but this should be, we've got play buttons up here, look. Right, let's do this so I can see how our thing is. Press go. So we'll put 5 into 1, radius 5, it's there, look, so 5 into 1, 5 into 2. Now, if we were actually going to do the calculation, we'd get 5 times 6 is 30. So that's our expected result. So then we add, we get 10, put that in there, add, we get 15. So then we'll put the 15 in both slots and add, we get 30, move it to out, and now we have R equals 24. So 48, and then it becomes 72, put 72 in both, we get 144, and next one is 15, what would that be? 90. We unlocked Robotron 9000 Plus. Oh, we unlocked the ability to control Robotron 9000 Plus using our computer. Spatial Invasion, Storage Cracker, and Masking Time. Let's try masking time. The length of our week is 4 days. Our weekdays are named 0's Day, 1's Day, 2's Day, and 3's Day. I hear some Earthlings number their Tuesday incorrectly. Tuesday. It doesn't really surprise me. Anyway, New Year's coming up and we want you to calculate the week date of everyone's birthday. We will give you the date and all you have to do is return the weekday within 8 ticks. So within 8 ticks, which means we have to limit our program to 8 lines of code, I presume. In this level you are given a number as an input and you should return that number modulo 4 as a result. The challenge is that you only have 8 ticks to output the desired result. Note that you don't need to change your hardware, you just have to figure out the trick to do modulo 4 quickly. Use this hint if you get stuck. Well, 0, 1, 2 and 3 with the days, which means the highest number we need, what's this? I'm a comment. The below calculates 1 plus 1. Put 1, or 1 is not to 1, not to 2, add. Well, that's basically what we just did in the last thing, innit? So we don't need that. Don't know what it's got to do with the current program though. So what do we want to do? We want to take input into reg 1. Then we want to put 3 into reg 2, and then we want to AND, which means we need to define AND. While let's do the others. And sub. That should be all of the computes done. Copy could do a bit of a while. Condition never. Honestly seems a bit pointless. So always is basically jump, go to. So test equal to 0. Test less than 0. Test less than equal to 0. Always, that's go to. Test not equal to 0. Test greater than equals to 0. Test greater than 0. So immediate doesn't want thingy in. Copy is too complex. We've done compute and condition. So our program into reg 1, put 3 in reg 2, and so what that will do, will take the number that you put in reg 1, put 3 into reg 2. Now reg 2 basically means that Let me look at this thing again. Ignore what the instruction's telling you. That's what we're putting in. And we're going to AND it to whatever we bring in. Which means that all of these bits here, doesn't matter what they are on the input, will get turned off because you're ANDing. And you only get a 1, a green, if both of them are on. So since we're saying that these are off, they're always going to be off. And these two are on, which means when we AND them to the input, if it's an off, it's off. If it's an on, then it's on. So these 6 are turned off, and these are whatever the input is. That's what we're doing with AND, which is the modulo of 4, because you can only ever get numbers 0, 1, 2 and 3, which are the remainder when you divide by 4. So we want to go to reg 3, 2, out, and in 5 instructions I think that is. We've got our readout here. That's probably what watched states is. There's our watched states. So we don't need to put it alongside this because we can read it here. So into reg 1. 1 now contains 28. Putting 3 in this one. And if you actually look here, these two don't match up with these two. So on the next tick, when we AND it, reg 3 should contain, well, blank, 0. Apparently that was correct. And we should end up with a 1. That's a 0 again. That's a 1 again. This'll be a 3. And that'll be a 2. Yeah, 2. So let's just run it at full speed, and we only had a few more checks to do. Program successful. Storage cracker and spatial invasion. Storage cracker. The security access door to the storage room is broken and it keeps locking out our old janitor inside. Locking our janitor inside. The door keeps changing the passcode. We need a program that can recover the passcode anytime. The easiest way to find the passcode would be to try all combinations until you find the right one. Although the broken mechanism does make a weird beep when your guess is too high, you might be able to use that to your advantage. You win this level when you output the correct passcode. No output will fail the level. Additionally, the input will be a 1 after a guess that was too high, and 0 otherwise. Well, it told us a tip there. The easiest way to find the passcode would be to try all combinations until you find the right one. Well, considering outputting the wrong answer doesn't fail, well, the easiest solution would be to... Okay, so this is where you have loops and stuff. Which one gets copied back to the program counter? 0 does. Handy that I coloured that line. So what we want to do, I mean the passcode could be 0, so we start at 0. I mean, we could just go to my label. I'm thinking label loop. Loop. I'm guessing that if you just write that there, as long as your program's a number below 64, it's just going to take it as an indirect, or what did they call it, immediate. It's going to take it as an immediate command to just copy that number back into the program. So you go loop go to, and that's now a loop. So whatever is in between that and that, that's our program. So we want to reg 3 to out. Before we do this, let's put 1 in reg 0 to reg 2, reg 3 to out, reg 3 to reg 1. Let's do it the other way around. So reg 1 contains 1 and it will always contain 1. We output what's currently in reg 3, and presuming that it's going to not be the correct answer, we then copy reg 3 into reg 2, which on the first loop will be 0, and then add. Which basically turns reg 3 into 1. Then you loop. So now it's a 1, so you output 1, add 1 to 1, which is copy your 1 into registry 2 and add 1 to it, which is 2, and you go around and try number 2. So in theory that's what my program's doing. So I put 1 in 0, put 1 in 1, then we output 0, copy registry 3 to registry 2, which is still 0, add to it, so registry 3 now contains a 1. Loop, go to, yeah, that worked. So it takes 2 instructions to go to loop. Outputting a 1, that turns it into a 2. Now outputting a 2, turn it into a 3. Yeah, go. This might take a while. And we cracked the password. It was 192 or something thereabouts. Of course, we do actually have feedback where if we guess too high, we get the number 1 out. So what you'd ideally do is you start in the middle, 128. Is it too high? If it's too high, you guess lower, so half it, so 64. Is 64 the correct answer? No. Is it too high? No, so you guess higher. And you know it's not 128. So we'd need a math thing to calculate halfway between 64 and 128 and guess that. And all we can do is add and sub in this little computer without changing the hardware anyway, because if we could change the hardware I'd probably do a divide by 2 and stuff like that, which we don't have. Divide by 2 or double it is... Hey, we're finished. It didn't even congratulate us. So that's the easy way. And that's why setting a complicated password is a good thing. Because brute force attack is literally just that. You start with one combination and just keep incrementing the guess by 1. Of course, there are other ways to crack passwords, like the dictionary method, where a lot of common passwords are in the dictionary and you just guess them all one by one, etc. The cargo hull has become infested with space rats. We have hooked your machine up to our advanced robot. Okay, is that where we've got the Mr. 9000 plus? Probably. We have hooked your machine up with our advanced robot and we want you to program it to shoot the space rats with lasers. Be aware that the laser can only shoot when there are no other laser beams already in flight. Check the robot page for instructions on how to programming. Here is a link to that. Yeah. Okay. So... Oh, I remember from looking at the options that we can use the keyboard to control him. So, tab. Apparently shot the box. So pressing a direction changes which way he's looking. And this looks like it's basically Space Invaders. Whoa! What did I press there? A space bar. I'm rotating. I can rotate. That's good to know. I mean, I haven't particularly had much need to rotate components yet, but let's just... I can rotate components. Okay, what's fire? Tab. And there's our laser, so you can't shoot again while the laser's in flight. So they come down like that. So there's a seeing option there. Seeing 33, space rat. Are they all 33? Well, the yellow ones and the blue ones are. Okay, how do we reset? Stop. So let's shoot, go up here and look left. Oh look! I think we should start our program by doing that. So let's just start that again. Shoot, then we'll press up 1, 2, 3, 4, 5, 6 times, then left. Edit memory. Shoot. How do we shoot? Is there a constant that we can set in here? The label doesn't work because anyway, so I want to go 6, which puts it in 0, then reg 0 to out. I guess we're going to have to add that one. It's, let's just click on one first. Reg 0 to out. There you go. So we shoot, then we move up 6 times. So let's just, I can copy paste. Let's move up 6 times, then turn left. Then we want to shoot 4 times. I'm gonna be a bit label left. I'm gonna presume from what we've seen here that we want to look left, then we want to into edge 1. No, we want to put .33. Let's put that in 1 then. 33 reg 0 to reg 2. Yeah. Let's do that first. Label up left into reg 1, then sub test if equal to 0. If there is, let's test if not equals to 0, because if it's not equals to 0, we want to look left, go to look left. Otherwise, we want to shoot the 4 times. And we want to it doesn't matter which way we're looking, we're just looking. That's left. Let's call this we have a go to, we don't have a return, do we? Because we need to remember where we were. Can we implement a remember where we were? Are we using everything up to 3? So in theory we can remember where we were. Do we have we don't have access to the program counter, do we? So we can't remember where we were. I mean, we could modify the hardware to connect it up as another memory address. Then we'd copy the program counter to, say, 4. I don't know, it's too complicated right now. So we do that, look left, we copy the whole thing. It's going to be pretty identical, but instead of looking left, we're going to look right. At the bottom here, left, go to. So we get into position, face left, wait till we see them, which we will right away, then shoot 4 times. Look right, wait till we see them, then shoot 4 times. Then go back up and look left, and so on and so forth. So in theory, let's look at this one. I know there's one there, but let's look at this one. Let's go through the program. So we shoot, walk forward, look left, put 33 in reg 2, copy in to reg 1, which is seeing 33, subtract, which should put 0 in 3 because they're the same, test if not equals to 0, go to look. Okay, so there's a problem. We want a look left, and look right. Try that again. Compare 33, we can see it. Go. Oh, we don't want to go to. Test. This is wrong. We don't want to go to. We want to put that in 0, then test if not equal to. If not equal to 0, you jump. Yeah. So yeah. So do the same. Put that there. Look right. Look to, right. I'm a little bit rusty on coding, as you can probably tell. So look left. We should go through because we're seeing the alien. So put 6 in there, which is shoot. Then you shoot 1, 2, 3, 4 times, and then well, nothing's happening because we're not doing anything. So we need to do this, else do that. So we need an else. We don't want to go back up here to looking left. It's pointless repeating that. So we want to test if equals to 0, put in shoot left, which is what I'm going to put in there instead. So if it is 0, we skip over to shoot left. Then we want to put look left back in there with a go to, and in here we want to enjoy the moment. So for reg 0 to out. So I'm going to copy all of this and go down here and replace these two with that, and instead of left we want right, like that. So if it is 0, jump to shoot right, otherwise put in 4, output it, and then go back to check in again. Right, so shoot, move up. Is there anything in front of us? Well, yes there is, so we jump over to here where we use the code shoot, do it 4 times, fall down here, look right, load up our check the eyes. We're going to fall through because we're not going to jump to shoot right because we're seeing 0 instead of 33, which gives us whatever that value is. We wait, then go back up to here, so wait, and everything moves 1. And shoot, 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 look left, go, just let it run full speed, shoot, 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 shoot. We unlocked run fast and a new entry in the book called the robot. Okay, the maze. This is what I was talking about here. You built the computer, but now you have to finish the maze. So, the maze is the name of a level. The fabled maze. If you solve it, you win the competition. Write an algorithm that gets the robot from the start to the exit. This level is hard. You probably want to write down the pseudo code for your algorithm before you implant it. In other words, use pen and paper to try and figure it out. Use this hint if you get stuck. Well, I'm going to load the hint anyway. Always following the left or right hand side of the maze will make sure you eventually reach the exit. The pseudocode for such an algorithm looks like this. Step forward, press use. See, I wouldn't have known to have to press use to exit the maze. Press use in case the exit's ahead. Turn left, turn right as long as there is no wall ahead. Repeat. Turn left. Oh, as long as there is a wall ahead. So, following the left-hand wall, you step forward, then you turn left. And if there's a wall in the way, you turn right. So you want to add change the order of these slightly. So the first thing you do is there a wall? Yes, turn right, because there might be a wall. That one wants to be in a loop, which is why I put it first. Did we turn right? Yes. Go back to the start. So we want the robot. We want that, and we want that. Huh. Oops, manual. Let's put. I want to keep the manual down here. Assembly. There is a const. Shoot 6. We could have done that in the previous one, so we could have said shoot instead of putting in the number 6 and so on. Yeah. So we want the robot. Let's start by doing this. Const right 0, const down 1, const left 2, const up 3. We don't need enjoy the moment. We do need action, and we don't need shoot. This is what we could do with a function. I want to turn right. How do you turn right? So step forward. So we want to store the direction somewhere, and a step forward is repeat direction. If remember from the Space Invaders level, you just press a direction and it turns into that direction without moving. So to actually move in that direction, you have to press it twice. So you repeat direction to move forward. Press use. Obviously, I'm not going to write a note for that one. Turn left. So if we turn left, let's say we're facing forward, which is up. We want to turn left. Up is 3. Left. You know, if you're facing up, to turn left 90 degrees, you need then facing left. So left is up is 3, left is 2. So we want to turn left sub 1. So subtract 1 from your direction to turn left. But if you're facing right, then you'll end up with a negative. So test for negative, which is test less than 0. Set it to 3. Let's try that in English. Set 3 if less than 0. Less than 0. Turn right. Well, that's obviously add 1 if turning left is sub 1. Instead of checking, instead of it is not 1 2 3. Instead of doing a check, you want to and it with 3 in both cases, because if you on a binary level, if you subtract 1, it don't matter what the other 6 bits are doing. The last 2 bits, they're going to either go 0, 1, 2, 3, 0, 1, 2, 3, or 3, 2, 1, 0, 3, 2, 1, 0. So if you mask off the last 2 bits by ANDing it with 3, yeah, okay. And then obviously use is 5, which you want to do as a separate action, not in the one that we're remembering. So we need to remember, other than the place in the program, which is done by the program counter, the only thing we need to remember is which way we're facing. What does a wall look like? Seeing 1 wall, so const wall is 1. We don't even need any of these. All we need to use is action and wall, and that's it. So what we want to do is change this algorithm. So the first thing we want to do is turn right, if wall, turn right, go back to the start. And if there isn't a wall, repeat direction. Do we want to repeat? Well, anyway, what would the next be? Repeat direction. Turn left. Use. They'll put it there. I'm going to say what we actually want to do is want to action, which is what we're calling it. If a wall turn right, action, go to start. So every time we turn right, we try and go through the door. So turn right, try and open the door. Turn right, try and open the door. Go forward, turn left, turn right, try and open the door. I mean, we could just put more use actions in there. Anyway, that's the program we want to write. This is the algorithm on how to do it. I need to be right back. I am back. Okay, so 10 right. Okay, so we can't store the value in 0. We can't store it in 1, 2 or 3 either, because we need to check what's in front of us, which means we need to put 1 into one of the 2 slots, 1 or 2, and into the other one, and when it does its math it puts it into 3, and whenever we try and put a direct number in there, an immediate, uses 0. So number 4, number 4 and number 5 are our only 2 memory slots we can actually use. Number 4 is direction. The direction that we're facing. So, start the actual program. Move 10 right, so let's go label start 10 right, add 1, so 1 sub reg 0 to reg 1. If I do this sort of thing again, I want to shorten these. Reg 0 to reg 1, reg 4 to reg 2, reg 4 to reg 2, no, we specifically need to put it in reg 1 because we're subtracting 1 from it when we're turning left. Doesn't matter with add, but with subtract it does matter which place you put them in. Okay, go to reg 1, add reg 3 to reg 4, reg 4 to out, I'm going to put a bunch of spaces under there. Right. Reg 4 to out, that's... we just turned right. Wall is 1. I've already put wall in 1 into 2, so into reg 1, sub, which subtracts 1 from what we're seeing, so we want to test to see if it's equal to 0, and if it is equal to 0 we let's make that a label 10 right. If it is if it's not equal to 0, go back to start, or 10 right. Let's make that a comment again. If it's not equal to 0, go back to the start. If it is equal to 0, if it is equal to 0, we're looking at a wall, turn right. Turn right as long as there is a wall. So I'm doing it wrong already. It's the first thing we want to do is put 1 into reg 2. Yes. Then we'll put into reg 1. And we want to test if not equals to 0. Okay, so we're looking at a wall. Put 4 into 1, add 1 to it, put it back into 4. So that's turning right. Forward is simply doing that. Step forward. Press use. Yeah, let's just, with the exception of starting with should we turn right, let's do the algorithm. Forward, label action, which label do action reg not to out. Yeah. So we want to add so that's not even turning right, it's incomplete. Add reg 3 to reg 2 so let's copy that, put wall there, yeah, 1, add reg 3 to reg 2, 3, reg 0 to reg 1, let's do it the other way around, and reg 3 to reg 4. Okay, so now that should be turn right. Label turn right. So add 1. And then and it with 3, copy it into 4. So, okay, So we turned right, and after we turn right we want to go to start, which goes back up here to see if we're looking at a wall. So are we looking at a wall? If we are looking at a wall, go to forward. No. If we're not looking at a wall, go forward. Otherwise turn right and go back to the start to look again. Right, there we go. Do action. Then it's turn left. Turn left is subtract 1. It's basically this with sub instead of add. And then go to start. Let's see what happens now. Okay, so we'll put 1 into reg 0, copy reg 0 into registry 2, copy the input into reg 1, sub, jump to move forward, which is probably going to mess up anyway because we weren't looking at what the register said we were looking. Reg 4, action. Turn left. Okay, now we're looking the way that it thinks we're looking. Is there a wall in front of us? No, so we should skip turning right, go forward, turn left. Yep. We are looking at a wall, so we turn right. Yep, we turned right. Check to see if we are. Skip ahead, move forward. Turn left. Okay, it seems to be working. Let's run at full speed. So take a step forward, turn left, turn right, turn left. It is turn left, turn right, isn't it? Yeah. It's it's not the best way to solve a maze because we're going down this thingy here that's got these little dead ends in it. We're going to go through all these dead ends and check them out. So now we're going to go up and go down that dead end. Still following the wall. Oh! I've got another map. Let's just pause it and then run at maximum speed. That's better. And again going in all the little dead ends, but it's following the left wall. and going in all the little dead ends again. And that just load the same map. I don't think the coins give us anything. It does seem to be counting them though. Congratulations, you won the competition, an amazing achievement. If you choose to go on to the rest of the levels, I will teach you about RAM, the stack, and function calls. Function calls would definitely have been useful on the Space Invaders level. And you will get to solve more interesting challenges like this one. But first you will have to build a better computer. Overture, which, if you recall, is the name of this computer that we built. It's what they told us what we were building earlier when we started building it. Overture was Overture was good as a first machine, but it is clumsy and programs get very messy. Well, yeah. To solve the challenges I have for you without pulling all your hair out, you will need something more expressive, the leg architecture. Do we have to call it leg? On the other hand, you could also retire, be proud and enjoy your reward of not being eaten. In the very, very first challenge, he basically said, we don't eat sentient beings, this is a test to see if you're sentient, because if you can build a computer, then by our law you are considered sentient. Okay. CPU architecture 2. XOR, byte constant, byte and, well, we made an XOR. Well, using the instructions of your computer. Build a new computer. Use the current one to calculate XOR. Using the instructions of your computer, read the input twice and XOR the two values together. Okay. So we're doing more of this crazy programming. In to reg 1, into reg 2, which we don't currently have, so input to reg 2 XOR them together. We don't have an XOR function. How are we going to XOR them together? XOR. How do you XOR? An XOR is A and B. No, A and not B. Not A and B. ORed. So instead of putting them in 1 and 2, we want to put them in 4 and 5. Copy in to 4 and 5. So can we not? Or NAND and NOR add and sub. So no, we can't not. So we're going to have to I'm gonna have to NAND to not reg 4 to reg 1, reg 4 to reg 2, NAND reg 3 to reg 1, reg 5 to reg 2, which we don't have, obviously, reg 5 to reg 5 to reg 2, yeah, so that's not 4 and 5, so it's the and. So now reg 3, we want to save it somewhere without saving over 4 and 5 without using 1, 2 and 3. So I guess we're putting reg 3 to reg 0. Let's label things A, B, A, not A, not A, B, not A, and B. So we already have B in reg 2, so it's reg 5 to reg 1, reg 5 to reg 1, B, NAND reg 3 is now not B. Reg 3 to reg 1, reg 4 to reg 2, which is A, and reg 3, which is A and not B, to reg 1, reg 0 to reg 2, which is our not A and B, or, and then reg 3, which is now I don't have a plus in a circle, so let's just use that A XOR B to our that uses every register in our program. I'm just going to press play. Byte XOR. Create a circuit that XORs 2 bytes bitwise. At least we're back to designing circuits. So like we have a byte OR here, what we want to do is XOR bitwise, which is just doing that. 1 and 1, 2 and 2, 4 and 4, 8 and 8, 16 and 16, 32 and 32, 64 and 64, 128 and 128, and then output them. Don't miss. Yay, and we unlock the byte XOR. So byte constant, equality, and byte AND. So create a circuit that ANDs 2 bytes bitwise, which we've literally just done with XORs. So boring and repetitive. We want to AND how long has this been running for? Nearly an hour and a half already. Signed less, unsigned less. Equality. Byte constant. Create a circuit that always outputs the number 164. $128. Right. Add that. 160. Okay, so 164. Let's stick that there like that. There. As tiny as we can make it. We unlocked something. Equality. Output green when both inputs are the same. Okay. Let's see. If you subtract one from the other, like that, then in theory, output 1 and they're both the same. Not. So when they're both when they're both the same, we should have 0. So now we want to OR, not 3 input 1 again, OR everything together and not it. Right, so here's my reasoning. If they're the same, let's say the number 64, 64 minus 64, sorry, 64 and 64, if you invert it negative, so you get negative 64. 64 plus negative 64 is 0. These should all be off. So we OR them all together. If any one of them is on, if that wasn't a 64, if that was something else, then you don't get 0. So if any of these are on, then that one's on at the end because it's OR. We're ORing them together. If any of them are on, you get a 1 here, a negative. Sorry, and then you invert it with a NOT gate, so you'd get a 0 on the output. But we're assuming that they're the same. If they are the same, you get 0 out. So all of these will be off. So this one will be off, and then that'll come on. Equality. Hey. So the output is 1 if they're both the same. Unsigned less. Create a circuit that outputs green when the first so we need negative numbers. Less. If the first is less than the second, how do we do this? If the first is less than the second, then if we subtract the second from the first, if the output is negative, determine if the first is less than the second. That, well, it should be. Yeah, it's not that simple, because if the numbers are bigger than 128, which there can be because we've got negative numbers there, there's 20 minus 90. Is 70. Or adding them together. 20 minus minus that is, that's 110, and it's rolled over basically. Is the first I don't know how to do this one. This is where I'm going to Google it. That doesn't even want to be on this screen. Let's stick that over there. Unsigned. No, let's do this. What is it? By less than let me just put you back on that while I less. So let's just try a few search things. Okay, I can show you this. Let's go back to screen. There we go. Digital comparator. So we've got a less than, greater than, check, digital comparator. So that's one bit. One, okay. Let me just hide this again. So I'm going to search for digital comparator circuit. We have a Wikipedia entry. Is this useful at all to me? No, because it's very limited. The pictures are one bit. That's the one that I've just loaded. Scrolling down a bit. Ooh, this looks like a nice page. And what's happening here? There we go. Let's see. Geeks for Geeks apparently is the name of the website. Magnitude comparator in digital logic. 1-bit magnitude comparator. Is A less than B? That's what we want. Is A less than B, which is basically just not A and B. And if we look at the circuit, not A and B is here. Are they NANDs? Two magnitude, a comparator. This is the truth table. So is A less than B? This is A, this is B. So B is 1. Yeah, this is very small. That's a little bit better. And then it gets more complicated. Scroll down. Okay. A1, B1, or A1 and not B1, or, oh no, I want the bottom one here, A less than B. Not A1 and B1, or, let's just have a look at this one. if this one here, if A3 is 0 and B3 is 1, if A3 is B3, that's an X 0, and A2 equals 0 and B2 equals 1. Okay, so that's the first bit, second bit, third bit. Let's put you back. Where's my pointer? Let's put Turing Complete back on here, and I'll pop this out to the other screen. Will be S. What is this? Okay. If I add oh screw it, it's too complex to try and set up while I'm in the middle of a stream. So we want to expand these out first, and apparently the first bit it's less than, we're not signed, we're in unsigned. It's less than that's less than that if we have A3 is 1. Now we're going to, A3 is the most significant bit on the nibble, so we're starting at the top end here. If A3 is 1, so that'd be our A3, and not, yeah, put it there. So that's one of the conditions. Oh no, hang on, I'm looking at the wrong one. If A3 is not, I want to swap those around. The next condition is if A3 equals B3, X0, if A3 equals B3 and on a 3 input and, let's put it there, and A2 equals 0, I'm starting to see a pattern. A2 equals 0, so that's knotted. Put that one there. A2 equals 0 and B1 equals 1. The next one is if A3 equals B3, A2, so we get our X no back out again, A2 equals B2 and the other one. Okay. So we're going to want 7, I think, of these X NORs, because the last entry is always just not A and B. So we'll want 7 put them there, of these x nors, probably want some space between them as well, like that. We want knots on all of these. So we don't need the least significant one, so we want 2 and 2. Hang on. If we're not in them anyway, let's just go with XORs instead. With gaps. Then I can push that up one, and then oops, I just go like that instead, except not 1, starting at 2. Then we want, yeah, we want 8 of these. What I actually want is an AND. So the first one is if A is 1 and B equals 0, no, that's the wrong one either. If A equals 0, which is the not, and B equals 1, then it's the same one again, so yeah. And then the previous one. So what we want is a bunch of ANDs here, probably 6. So it's that and the previous AND. In that one. So the second one is that. Let's put our let's get rid of that, bring them closer. Let's get our ANDs in. 1, 2, 3, 4, 5, 6, 7, 8. Let's center them. Yeah, we're going to need the space with this. Oops. So let's connect. Are we gonna? Oh, yeah. That's wrong because the first one's from here. There, so it's like that. Let's go with the bottom one then. So then it's that one and that one, that one and that one. That one and that one. 8, 4, 2, spaghetti. Then we want to or them. Oh, that way is neater. The pattern. So does it work? Determine if the first input is less than the second. No, so it's off, good. Yes, so it's on. That unlocks something called an unsigned less. And what's this? A signed less. Let's go like this. Control C. I can't copy paste between levels, can I? Let's just try copy. Paste. Copy. Paste. No, it's not copy and pasting, so I have to build it again. But this one is signed. But instead of a value of 128, it's got a value of negative 128. So I reckon that what we want to do is put them there like before and one there instead. We want to invert. We want to invert the most significant bit. So instead of it equaling negative 128, it equals 128. We don't care about the actual number. What we care about is if one's larger than another. So what we want to do is convert our number not into its negative, but into a like an offset thing. How do I explain this? Also, with all these NOT gates here, I just realised I could have just used NOT. Like that, and then instead of all of them, I won there. So let's go back to the other level. Instead of all of these, I'm going to be careful not to sever it. I'm going to put that there. Then get the by not, yep. Ah. See? Right. So what we want is, what do we want? I forgot now. What we want is a bunch of XOR gates. Then a bunch of AND gates. Then we wanted a bunch of three input AND gates. Then an OR gate there and there with a 2 input here. And then we rebuild the pattern. It was like this, except that one goes to the previous, like that. They go on them. This first one is just like that. This one, let's go there. It's that. Then it's there, there. 32, 16, 8, 4, 2, 1. Play. Yeah, so what we're doing is, for example, is it 0? All of these would be 0. If it's 0, we invert that, which adds 128 to it. So it becomes 128. So anything less than 128, the number works as before, whereas, for example, 127 is one less than... Sorry, minus 127 we're adding 128 to it by inverting the last bit anyway, so 0 becomes 128, 1 becomes 129, minus 1 becomes 127, because minus 1 is basically all of them turned on, because it's minus 128 plus of all of these that add up to 127. So, yeah, it works. Wide instructions. Create a device that saves the program output on even ticks and outputs both bytes on odd ticks. So we have to create a circuit that saves register. We have to have a switch. I don't know which way round it wants to be. So on even ticks, you save. Let's put not. Hang on a minute, what's this? Demux do. And load. So when it's a 0, it's a 1. That's backwards, I think. The top one goes like that. Probably. So on even ticks, that's a 0. We save. And then we load, which outputs the current one to one of them. And okay, maybe it was the right way around. Save the byte, yep. Then output both bytes. Save the byte, output both bytes. Unlocks more program blocks with 2, 3 and 4 byte outputs. Wire spaghetti! Okay, it's our computer again. Finally, it's time for you to start building leg. The leg architecture is a computer that takes 4 bytes per tick from the program. The first byte describes the operation called the opcode. Since many operations take 2 arguments like add, or, etc., the second and third byte are for arguments. So first is the opcode, second and third arguments, and since most operations return 1 result, the 4th byte is for the result. Okay. The following are the setup steps that need to be done in order to complete this level. 1. Click the schematic icon, which is the floppy disk, and create a new empty architecture. New leg, because it told us leg. Okay. I can't zoom out anymore. We literally only have these things, and that's in my way. Place a program block with 4 byte output. I can't tell where the center is, but that's okay. Place a program block with 4 outputs, yes. Place a counter, set its increment to 4 and connect it to the program block. Counter, set its increment to 4. Add 6 registers or custom components with registers. Memory register. Let's go with this one. Leave some space. How's the spacing there? Let's grab another one for measurement. That's 4, 4, 4, 4, 4. So they're all equally spaced. Click Edit Watch States on the program component and connect registers 0 to 5. That's 5. Connect the counter to 6 and output to 7. Well, there's output to 7. Yeah. Okay. In this level, the opcode is always 0. This means we add argument 1 and argument 2 and save the result in the destination. The value of the argument or destination refers to one of these places. So we've got the program counter on this at 6 instead of the input output. If you remember with a controlling the robot level, I commented that we didn't have access to the counter. In this one we do. A bit odd that it's on 6 to move what was on 6 to 7. I would have put it at the end. But it's telling me to do it this specific way around, so in the next level you will implement more opcodes which requires a different ALU than the one in Overture. But we haven't built a different ALU yet. So let's... What is... Okay. Add. Let's go back. Add is yeah. The opcode is always 0, so we always want to. It said we've got this one, output's a constant, so we want constant to be 4, which is add. It says place the registers, but we want to connect. The opcode doesn't matter. We want to connect 1 and 2 to the output. That's always on. Oh. Oh. So we don't care about the opcode yet. This is an address for which one to load. But what we'd need to do is we need to put a pair of demuxes on like this. Not there though, left a bit. Just wide enough for one way to get through. And then we'd actually, instead of connecting it to load and save, what we'd have to do is add a switch here. Consider one of them the first argument, so you'd connect the first one like that. Why is that orange? No, not like that. Like that. Sorry about that. Apparently my internet hiccuped. And then you'd connect that like that. So that makes this useless. The opcode is always add. Unless it puts other things in there. There's the let's get rid of that. And let's go back into here. Since we have this anyway, let's copy it. Let's name it something else. Instead of register plus, I want to call it a register duo, which should be a hint of what I want to do. And instead of a switch, I want to add a second switch. A second output. Another input. Like this. What's this? That's save. So that'll be destination. This is load. So we have opcode 1 and opcode 2. No, not opcode. Argument 1 and argument 2. So this is going to be load 2. And load output 2. Always output. I'm just going to change it to that one, save value. Load output 2. Okay, and then load 1. Output 1. Load output 1. So we've got load output 1, load output 2, save value, and always output. Just close that. So these, I want to use these instead. I probably want more space as well. Okay. It's in the wrong place. And while I'm at it, let's also make component factory a new component. Let's put in one of them, one of these, like this, with a byte input here. 8 outputs there, and let's lower that slightly with a bit input like that. There we go. And this is basically what I would call an address decoder. 3 to 8 line. So let's just give them names. 0, 1, 2. Oh. 3, 4, 5, 6. Instead of 6, it's counter, and this is, that can be output. So this is reg. This one is then disable, and this one is address. Might need to change that to something else later. For example, if there's an opcode that doesn't want the address decoding, then I could potentially have opcode come straight into here with whatever logic to turn it off, rather than a disable bit. Depends. So if we go back to here, instead of new circuit, I'm going to call it address decoder. Yeah, AD for address decoder. What did I press now? Okay, never mind. Back to level. So instead of this, I basically have those in a chip already. Which means there's a bit more space to come this way. So we also want input to be addressable like this, Okay, so first one was load 1. So 1 and 1. 2 Oh. What have I done? Ah! And then these two, we want one for the program counter, which means I want let's copy copy register duo 2 it's switch duo. So you want that. There we go. Data in, data output 2, data output 1. We don't really need an always out. Oh, better. And OR gate, yeah. So instead of load 1, we want enable 1. Enable 2. And just enable. Right. And if I go back to the level, we want, what's it called? This one, switch duo. I'm going to put it here. And then another one there. And I put this this is input whatever, like that. So then this one connects there, that one connects there, this one to there, and this one to what? This one to there, this one to there. I'm going to put one of these this one to here and this one to here. I can get rid of that. Yeah. Let me have a look at the thing again. Was the first? There we go. So what colour do I have that's closest to that? With the data one, don't we use data one? So let's use this one. That's not even the right place, it's this place. Like this. No, that one. No, there's that one. And nudge up one. If I put it in line with the first register there, like that, then let's go with this colour. Give a slight gap. And let's go with, that's it, like that. Memory addresses, registers, counters, input, output. We are incomplete because we need a destination address. Let's put that there again. 1, 2, 3. Something's wrong. Someone managed to do that wrong again. Oh yeah, because that'd be that. Destination, we need to connect this up as well. Program count, move that out of the way. Program count is also a destination, so I actually want to bring this somewhere around here. because that's not a valid option. That wants to go to there. Yeah, that one's a special output for enabling the output of that. So this goes to there. And while that is correct, we want to just clear it for now. We want to go down. No, yeah, you can go across it. Like that. Oh, bollocks. Oh, double bollocks. Okay, we don't want it purple though. Mm-hmm. I don't know if we're going to need that always out on anything else. Well, on these anyway. This don't matter because I could just connect that straight up like that. Then our input goes in like that. I'm tempted to change this simply by moving that like that. Has data in. Ugh. So this up one. I don't want it purple though. I should probably give the program counter a unique colour. I probably want to use that one for this. So I want to use that one for the opcode when I do an opcode, which means a unique colour could be this. Yeah, maybe. How's this looking? Oh yeah, I swapped these around. And I don't want them that colour. Like that. Ah! Yeah, like that. So then that goes in there and leaves the bottom one unused on that. Great. I can't really condense that anymore, can I? Because they're from different things. If I wanted to try and put that in directly, spaghetti. Anyway, I think that should now satisfy these conditions. Oh, no. I need to connect these back up because I deleted them. Yeah. It's still not working. Argument 7 means read from input, but input is not enabled. One or two. Throughput to enable. Yeah. Argument. It's on there. It's simply an OR gate lock. it should be working, but it's not. Well, there's only one thing for it, isn't there? Give me an OR gate. Turn that back to norm. Okay. Why is my switch duo not passing through the enable line? Higher spaghetti. Opcodes. Implement the following opcodes. The opcode not ignores the second argument. This is where you design a new ALU. Where instead of a 4 there, you take that up to there and let's make this neat. Not quite that one there. Like that. And however far down it wants to go, let's just leave it open-ended like that. In fact, let's move this up. Rearrange things. Probably at some point. And slightly to the right. So implement opcodes. Still don't get why switch duo isn't doing its OR gate. Oh. What was it? Yellow. Yellow was the first one. And this screen was the second one. With green, yellow, and it's still not lighting it up. I don't get it why this OR gate isn't working in the friggin' custom chip. Oh, because that's an in. I want an out. stupid simple mistakes like that. Now you've got a conflict here apparently. We can't have that in there. It's not a huge loss. I was just trying to save some space. So, we need a new ALU. So, first thing is, in fact, just make a new rename to leg ALU. We want byte inputs, 3 of them. They want to be called opcode. arg1, arg2, and byte output giving room. Okay, we also want this there, so I want to delete that ALU and use the leg ALU. We want add sub and or not XOR. Let me just write that in a notepad because it's going to disappear when we enter the ALU again. Add sub and or not XOR. So we want add, not a bit, add, but we want a sub. We don't have a sub, we have a neg. Then there's and or not XOR. That's a weird shape for a chip. And or not XOR neg let's move these all down a bit. We want 2 switches there. So I want to go yellow. So I want to go like that with greeny like that. We want this further that way slightly with the opcode colour, and this as the output with switches like this. Hug. I know, it could probably be closer. You only need the one switch there with an OR gate. Do we want... I can't bring in a custom component, so I'm going to have to use an actual... I don't want them pink though. An actual D-box like that. Yeah. Leave a little space just in case. I can push these down a bit if I need to. In fact, let's do it now. I want to go down one there, which I'll need to do in green. Down one there. Down one there. Like that. So add or subtract. You want add subtract and or not XOR, which leaves space for 2 more instructions. And honestly, if I was doing it myself, this is not the order of where I'd put everything. I'd probably also include NAND and NOR. Do I really need to though? XOR flips and masks, or opposite masks forces bits to turn on, not inverts, so you can do most of what you need to do with what's here anyway. Okay, so this should now be the leg ALU. So go. Got 2 more things to do. I've been streaming for nearly 3 hours. I'd call it quits, but let's see if we can finish this computer. It shouldn't be too far. I think sometimes it's useful to load values directly from the program instead of the registers. This is called loading an immediate value. In the leg architecture, we signal when we want to do this directly in the opcode. We can do that in the following way. When the 8th bit of the opcode is green, use argument 1 as an immediate value instead of a register address. Okay, so and then the 7th for argument 2. So star toggles between immediate and register. So what we want is to use these disable lines here. What we want is we want probably a custom component at some point. We want a pair of switches. You know what? Let's start off by raising these. Then we raise this. There you go. Because what we're going to want is a switch. No, this isn't actually as nice as I thought it was going to be. Because switch is that bobble on top, so if I put that here, it uses the top one as a switch. So let's pull it down slightly. Put a switch there and a switch there. Yellow one. Like that. And we want the opcode. We do actually want this. There, like that. And then we want we want this one for here and that one for here, I think. And whoops. up there like that, but also if turn off the colour, we disable that if we're putting the thing straight on, and we disable that if we're putting the thing straight on. Probably we want to disable that later. So that should be that one, I think. Add if statements to your circuit. For the if statements, the two arguments are compared, and if the condition is true, the counter is set to a jump address. Add the following previous opcodes. Add 32. 32 equal 33 not equal less not less greater or equal. Oh, use unsigned less for the comparison. Let me write these down in my notepad. So it's an offset of 32, which means we're going to edit something, so that's equal, not equal, less than or equal, greater than or equal. So the first thing we want to do is go back into here and disable it if the 32 line is set. I shouldn't have left. But then we also want to create a new component. One's called cond. Leg. If. Because it said make an if thingy, so we need 3 byte inputs, which are opcode arg1 arg2. We want an output bit, probably, if it's like the other condition, that next to the program counter. Which is currently set up to destination. Anyway, we want unsigned less. I think we want 2 of those and an equal. We also want this up one on the opcode there. So we want, let's do what we did on the previous one, opcode, yellow. I want it like that, I think. I'll move them around in a moment. What we want bring that a lot over this way. True. We want not 32, and I don't want it like that. We'll probably want to go with debugs. Yeah, if I put that up there, it's gonna do weird things. So leave this in here. So if 1 less than 2, if 1 greater than 2, so we want I look at the things again. We'll have yeah, okay. We have want an and. That will probably want a few ands. Let's put it back over there for a minute. I want a bunch of ors. We want there. We want an or on this one and this one, and a not on this one. The second pin. So it's equal to, hang on a minute, let's put that up to there, equal to, not equal to, we then have or equal to, and then I have if input 1 is less than input 2, which goes like that. Then we have the greater than or equal to. So 1, 2, 3. Again, 6 conditions. So there's room to add more. That's probably right. Probably. If equal to, if not equal to. Yeah, since they're an and, it only looks at it if it's specifically set by the opcode through the demux. Equal to, not equal to, less than or equal to. Greater than is basically a backwards less than, so there's greater than or equal to that. that should be our leg if, and I don't want to put it there exactly. I mean I do, but I don't. That's what I'm going to have to do. Spread it slightly like that. Given the order that these are connected, the orange one really should be before the yellows, not after them. There. So if look at the problem again. Jump address. So we want as I thought we would need another one coming down here to another switch. Let's just cancel that for a moment because it's going to be in the way. That way, yeah. This goes to there, so let's bring it this way around. And this goes into there. This will already be disabled internally with its switches if the opcode contains a 32, which activates this thing. So we then need to have an OR gate here. Wrong colour. Where this goes there, and this one goes to our OR gate. Like that. So if that, switch on that and this. So this should be conditionals complete. It's not. What's wrong? if equal 0 and 1, 0 and 1, jump to 24. Well, they're not equal, so why is it coming out as true? What did I? Let's go back. Let's go back in, because okay, clicking on it just cleared it anyway. Let's try that again. If reg 0 and reg 1 are equal, jump to 24, it's green. Equal is the top one. It's saying they are equal, it's saying they're both 0. It's probably cleared anyway. If opcode 32 yeah, that's right. Why is it not? Opcode 32, written 0 and 0. Seems to be a problem with this. As it's saying, it's not outputting anything. It should be outputting 24. Not sure what these numbers on the end are. Could be delay. It's probably a obvious problem. Just don't see it. Also, that's not quite right because I wanted it. Oops, not down one. Like that. So why isn't it doing what I think it should be doing? Opcode 32. If not equal to, well, they're the same, so opcode ADDI. What is our opcodes anyway? Are we defining the opcodes in here? Well, this is it's immediate 1, immediate 2, reg 0, reg 1, these aren't the opcodes, these are addresses. ALU if what was it? Add sub and it was, I don't actually know, and or not XOR. And or not XOR like that, and or not XOR equal not equal it was less than or equal, that worries me slightly. Add not and or sub XOR, turn it on, new rule. Oh. Greater than greater or equal So not into the demux, which means it only turns on, it only works if that's on. And our equals working. The not equals working. So I can only conclude I did something wrong somewhere. Equal, not equal, or less than, which goes to the equal up to here and up to here, greater than, which goes to there, and or. So that should be correct. If equal, argument 1, reg 0. For some reason. Oh! That's loading. That's, yeah, okay. Why does that have a 24 in it? Mm-hmm. Okay. When does it get a 24 in it? It gets a 24 in it on the jump to 24. Why is it being set to 24? The save line wasn't active. I mean, that's simple enough that it shouldn't be messed up by this. So why is it? Let's include a 10 destination off. Not if you're ifing. Let's just do that. That might help. Yeah. Congratulations, you finished the leg computer. I will show you some upgrades you can make on the path to implementing function calls, but from here on the details are up to you. I won't tell you what opcodes to use and so on. NAND score. You now view the NAND score circuits and components. Copy is just add with the second argument being 0. In any case, I think that's it from me. So, signing off for the night.